Good day, ladies and gentlemen. This is our second lesson on linear relationships, and in this lesson our objective is going to be able to determine the initial amount, or y-intercept, otherwise known as b, of a linear relationship, and use it along with the rate of change, m, to write appropriate linear equations. In order to do that, there's a couple things you have to remember. First is that linear relationships are repeated addition patterns. They are the result of a constant amount being added or subtracted over and over again. So another way of saying that is they're increasing or decreasing by adding or subtracting the same amount over and over again. They're also known as first degree polynomials. That's going to mean that their exponent of x or n or t, whatever it is we're measuring, is going to be raised to the power of 1. When you're raising a variable to the power of 1, we usually don't show the power. We just write it as either x or n or t, because we know that if there's no power indicated, then it's automatically a 1. Kind of the same thing as a coefficient. Linear relationships are most often seen in the form of y equals mx plus b. A more appropriate form that you will be able to use for all the other relationships we do throughout the school year is to call them y equals ax plus b. And the reason we would call them ax plus b is because a is the first letter of the alphabet, so we use it to represent the first numerical value in an algebraic relationship or expression. B would be the second numerical value as your eye reads the relationship from left to right, being the second letter of the alphabet. If you chose to reverse the numerical constant, or what we're going to come to know as the initial amount, and you wanted to put that first in your expression, which we know we could do through the commutative property of addition, we would then call the initial amount a, because it's the first letter in the expression. And then we would refer to the rate of change, the amount being multiplied by x, as b, only because we reverse the order of the expression, and we put, using the commutative property of addition, and we put the variable term second in that relationship. So in all equations moving forward, a would indicate the first position of a numerical value in that expression or relationship, and b would indicate the second position of a numerical value. It doesn't mean that things are changing in terms of how we're supposed to interpret what an a and a b are. Again, most often you're going to see it as y equals mx plus b, and because the first degree polynomial, technically there is an exponent of 1 attached to the variable x, but we don't write it because we know that there is a 1 when we have no exponent at all, so it's usually y just equals mx plus b without the exponent there. In other countries, we know that they don't call the missing amount x, or the number that they don't know they call n, which makes sense. And 90% of the time, the variable x, the thing we're measuring, believe it or not, is going to be time. We're almost always making measurements or predictions based on time. Linears may seem like a result of multiplication, so often people are like, wait, Tooch, mx plus b isn't m being multiplied by x. Shouldn't we identify this as a multiplication pattern? And the answer is no, because one of the things people forget when they learn multiplication is that it's just repeated addition. So although it appears to be multiplication because it's m times x, please know that multiplication is just repeated addition. That's why these are repeated addition patterns. Because of their constant amount of change, because they're going to be constantly going up by the same amount over and over again, they're going to graph as straight lines. They're going to appear as straight lines. So if I jump to my calculator real quick, and it's always a good idea to clear out your screen when you turn on your calculator. It's even a better idea to reset your calculator, which would require you to hit the second function key and then the plus sign. It's going to ask you what you'd like to do. If you choose choice 7, reset your calculator, and you scroll to the third tab on the right, reset all of your calculator's functions, it'll bring it back to the factory settings. You just need to hit reset in that next tab, and it'll make sure that if anything happened to your calculator while you were walking through the halls or what have you, that it'll go back to the way it was initially intended to be used. So now you can go to your y equals key, and if you played with this a little bit, you'll see that you have all these relationships set up for you. And if you did something simple like 2x, y is equal to twice the value of x, and you graphed it, you would see that it makes a straight line. If you did something like y equals, and the second one, you can scroll down to the second relationship and do 3x, y is equal to 3 times the value of x, you'd see that that's going up even faster. It's a little bit steeper. And you can start to mess around with some of the investigations we're going to make today. So you could do like, what if I did 2x, y is equal to twice the value of x plus, let's say, 4. And you'll notice that when you graph that line, you would hit enter or either graph. The black line, sorry, I got to hit graph, is going to be shifted up in comparison to the blue line. It's going up the same rate. It's twice the value of x, but we're starting it with an initial amount of 4. And you can continue to mess with that. We see a lot of fractional rates of change. So we could say y is equal to 1/2 or 0.5, the value of the variable x. And I'll do minus 4, so that shifts it down the graph a little bit. And you'll see that that's it's going up much slower. It's the flatter line, but it's starting the initial amount 4 units down on the y-axis. And other things you could do, you could make the relationship decrease. You could say y is equal to negative, make sure you have the minus sign, 2x plus 3. And our green line is going to be going down and it's intersecting the y-axis, so the initial amount is positive 3, and we'll be able to mess with that. But what you notice with all these first-degree polynomials is they all make straight lines. When we get a chance to mess with that relationship as we move forward, take a look at this orange one. If I did x, say, squared, once I change the exponent, the behavior is going to change, and you get this what we call parabola. And if you did something like y equals, let's say, 8 minus x squared, you'll get a parabola going down, and we'll have a negative result. And we see that a lot in relationships that have to do with launching or kicking or flying. Because we live on a curved planet, things actually don't go up and down, straight up and down. They actually go up in a curved pattern up and down. So we'll make those investigations later on. And as you continue to change the exponent, you'll see things get really kind of funky, which we'll see later in the year. So I'll do one more for you. If I were to do x to the third, power 3, you'll notice that this relationship makes like an S pattern. I'm going to reset my calculator because that's so many different things. It takes me forever to delete them. So I'm just going to go back through that reset process, and that will get my calculator to clear all that information out, and we can get going with our linear investigations. For today's objective, being able to observe the y-intercept, or the initial amount, and write an appropriate linear relationship along with the rate of change, our essential questions are going to require, so if I go backwards and look at number 24 for today's work, it says that we have a linear relationship, a repeated addition pattern, where the amount of money in the savings account is being increased at a constant rate of $80 a month. And after 30 months, there's $3,400 in it, otherwise known as 3, 3,400. 30, excuse me, 3,400. And what we're going to do with that is we're going to identify the rate of change, $80 a month. That's our M for our linear relationship, the constant rate of change. And we're going to determine the beginning amount. We don't know the beginning amount at this point because what we only know is that after 30 months, the result was that we had a total of $3,400. So if you think back to the little bit of work we did on verbal equations or solving common word problems, one of the things I told you guys to do was that you had to decode the relationship. You had to underline circle star information. And I also had suggested if we don't know an amount in mathematics, typically we call it x, and that if we're not sure where to start an equation, we have a good place to start with the total. So if we want to write a linear relationship, we're always going to start with the most common form, y equals mx plus b, and we're going to substitute in the quantities we have for some of those missing amounts. So we have 4 missing amounts, y, m, x, and b. We know that the total observed, or the measured amount at this point in time, is $3,400, so we put that in place of y. We know that the rate of change is 80. That's what it's going up by over and over again. And we also know that it has gone up for 30 months. So we put that in place of x. 90% of the time, the x variable is representing time. We just don't know where this account started at b, the beginning of the initial amount. So what we're going to do is simplify and solve for b. $80 a month times 30 months is an increase of $2,400. And if we subtract that away from both sides, we find that the account began with $1,000 in it. This was an account somebody opened with $1,000 and planned to save $80 each month. And we can write that as y equals 80x plus 100. Or, in a more productive manner, we might choose to use the commutative property of addition to rewrite it as the amount in the account, put a in place of y. That's a more realistic variable. It describes this relationship much more completely. The amount in the account is the result of starting at $1,000 and adding $80 each unit of time, t. I don't like using m there for months because people get confused with, was that the rate of change m or is that months m? Like, what just happened there? So we almost always use t for time because m gets confusing, and if it's in seconds, s gets confusing. S often looks like a 5. So t is the most common variable that we substitute in place of x, especially when it is representing some unit of time. So in addition to being able to take information from a word problem and write a linear pattern, a repeated addition pattern, we also want to be able to do that graphically. If we're going to write a repeated addition pattern, we need to know that we're talking about a relationship where y equals mx plus b, or technically a first-degree polynomial that's the result of repeated addition. Well, Tooch, doesn't it look like we're multiplying? It sure does, but multiplication is just repeated addition. The two most important variables are going to be m and b, the rate of change and the beginning amount. So in this particular relationship, if you go back to yesterday's work, we could determine the rate of change from a graph given 2 points, 2 observed measured amounts at some point in time. In this particular graph, if I just counted how the relationship is changing rise over run, I would notice that from the 2 points I've given to work with, it's decreasing by 600 feet in 45 seconds. So I was just able to observe the scale and notice that every box was 200 along the y-axis, and 2, 4, 6, 3 boxes is a decrease of 600. And on the x-axis, the scale was going up 30 seconds every 2 boxes. Therefore, it's 15 seconds per box. So I had 15, 30, 45 seconds. The rate of change in y over change in x, change in measured amount over change in time, or how many times it took us to have that measured amount change, is a decrease of 600 feet in 45 seconds, which on calculators would simplify to negative 40 feet every 3 seconds. So this is going down 40 feet every 3 seconds. And you can imagine if you drop the ball off the top of the middle school and you counted how long it took to hit the ground, the middle school is about 40 feet high, and when you released it from your hand, it would go down 1,000, 2, 1,000, 3, 1,000, and hit the ground. So there's our rate of change, and graphically to determine the initial amount, it's a lot easier than doing it in an equation where you actually have to compute it. If you have a picture, just observe where it starts at. The observed starting point is going to be along the y-axis. That's time 0. And in this instance, it's 2,000 feet. So something starting 2,000 feet high when we first begin to observe it at time 0. And we notice that it's going down 40 feet every 3 seconds. So the relationship, when we substitute in for the rate of change m, along with the initial amount that we found through observation, is that y equals negative 40 feet every 3 seconds, starting at 2,000. And if you use the commutative property of addition to reorder that expression, it makes a lot more sense to say we're starting at 2,000 feet and we're decreasing 40 feet every 3 seconds. I've grown to love this presentation. To make sure that we're not entirely cramped for time, I'm going to work backwards through some of the skills throughout the worksheet. In section 1, Roman numeral 1, number 3 suggests that the amount left to pay for a used car loan balance over time in months can be represented as the balance B is equal to a decrease of $200 each unit of time, which in this case would be months, starting at $8,000. So we borrowed $8,000 and we're paying it back $2,000 a month. We could have rewritten this and suggested, why don't we say that it's started $8,000 that we owe and decrease it by $200 that we pay every unit of time t. And that would have been possibly a more interpretive presentation. But for what we have here, y equals mx plus b, it's not a bad idea to write y equals mx plus b across the top of the relationship. And understand that the rate of change m is a decrease of $200 every 1 unit of time, in this case month, and at the beginning amount, the amount that we began borrowing the loan at was $8,000. If we look at number 6, it suggests that the height of a wheelchair ramp versus the length measured in feet. So wheelchair ramps have certain code that you have to abide by when you build them. If you've ever seen a wheelchair ramp that goes into a restaurant or a house, it goes up at a pretty predictable rate. And that's actually been predetermined as to what it has to be. It can't be too high, you'd never be able to push them up. It can't be too long, you'd never fit it in front of a facility. And it suggests that the height should be represented as 1 foot of increase going up for every 4 feet that you go over. If you write y equals mx plus b across this relationship, you would recognize that the rate of change m is 1 increase of height for every 4 feet of length, change in y over change in x, and that your beginning amount is simply 0. You're going to start at ground level, and then you're going to increase yourself to whatever the door height is of the facility people are trying to enter. So the beginning amount in that instance is 0. When you look at number 9, ladies and gentlemen, it suggests that the cruising height of a cross-country flight, where the altitude is measured compared to the time. So often the way that this is described is, if you've ever taken a flight before, when you take off, you have to go up for a while, and then so there should be a plane here. Hey, there's my plane. I hope you like it. Once you have increased from the airport, you arrive at some point at what's called the cruising altitude. And the captain usually gets on and says, ladies and gentlemen, we've arrived at our cruising altitude. You may take your seatbelts off and relax. And you stay at that height for quite a period of time, and then eventually go down. So we're talking about that constant height where it doesn't go up or down at all. It stays there for the whole period of time. If you're going across the country, it's probably about 4 hours. So if we say y equals mx plus b here, what you notice is that there is no x variable. So technically, the rate of change must be 0. It's not changing at all while it's cruising. It's staying at that same height. It doesn't go up or down at all. The beginning amount when you're cruising is 25,000 feet. So when you start to cruise at time 0 of cruising time, you're at 25,000 feet, and you stay there for the whole duration of the cruising portion of the flight. When you go backwards and you start to apply those considerations to just regular relationships without any context to them, which is super boring, but it's what we typically do. We have you practice things mathematically, not knowing what you're going to use them for. That's ridiculous. In number 1, y equals 2/3 x plus 4, the rate of change, the amount being multiplied by x, what we're repeatedly adding over and over again is 2/3, rise over run, and the beginning amount of this relationship as 4. At time 0, we start at a measured amount of 4. In number 2, y equals mx plus b, we kind of do the same thing. We recognize that when we make our observation, what we notice is that there's no coefficient on x, which automatically means it's a 1. So the rate of change is 1 over 1. It is going up 1 measured amount every 1 unit of time. And for this particular relationship, the beginning amount is negative 4. So it's starting at time 0 at a measured amount of negative 4. I'm going to ask you to pause the video and try to do 4, 5, 7, and 8, and we'll see if you're able to get the correct interpretations of what m and b are for each of those linear patterns. Is that for those 4 linear patterns. In number 4 itself, the rate of change is 3, and the beginning amount is 0. And we like to write rate of change as a fraction. That way we can identify the rise or the increase in the y variable every unit of time. And the beginning amount we always like to write as happening at time 0, the initial amount. And for number 4, the beginning amount is a measured amount of 0 at time 0. For number 5, the rate of change is negative 1 over 1, and since nothing's being added to the relationship, the beginning amount would be 0, 0, 0, similar to number 4. In number 7, there is no x variable, therefore the rate of change is 0. There is 0 change happening over the units of time, and the relationship is starting at negative 2. It's starting at negative 2 and it's staying at negative 2. So if a cable was to be put underground for some sort of electrical system, you could imagine that if it was 2 feet under, you'd want to keep it 2 feet under the whole time. You would need to know where that is if you ever had to dig in your yard or in some community space. You need to know where that electrical cable is so that people don't get electrocuted and die. It's always 2 feet underground. In number 8, ladies and gentlemen, there is a relationship that has $1,500 describing it. There is no rate of change. There's no x variable, so the rate of change must be 0, and it's $1,500. So a lot of people like to save money. Years ago, my parents would save money, and they just put it in like a can in the house. They didn't trust the bank. And if you put your money in your bank in a savings account, it should grow. They give you what's called interest. But if you put it in a can in your house, it should stay the same. So my parents' $1,500 in the can in the house was worth $1,500 when they put it in the can. It was worth $1,500 4 months later. It was worth $1,500 7 years later. It just never changed. There was no rate of change there. Cool. Take a look at the second skill. And in the second skill, what we'd like you to be able to do in terms of writing linear relationships is be able to take the components of a linear relationship and put them into an appropriate equation. So if you take a look, we'll work backwards again at number 18. The weight gained by a Mastiff pup per day, the rate gained is 1/3 of a pound per day, and the initial amount is 8.5 pounds. So Mastiffs are giant dogs. They almost look like horses. Go online and check some of them out. They really are literally that big. And 1/3 of a pound a day is a tremendous amount of weight gain. So our rate of change, our variable m, is 1/3 pound per day, and our initial amount, the Mastiff pup was born at 8.5 pounds. It's a pretty large puppy. And we can write y equals 1/3 x plus 8.5. Or if you prefer, you could have more appropriate real-world variables, and you might want to say we're really measuring the weight, called w, and that is starting at 8.5. You might want to use the commutative property of addition to reorder that expression so it makes more sense. And it's being increased by 1/3 of a pound. And instead of saying x variable, in this case you might want to use d for days. We often use t indicating time, but d is an easy variable to work with, so I think that's probably how I'd write it in real-world context. When you take a look at number 15, it suggests that Brittany earned the amount of money earned by Brittany, who just got started babysitting per hour, is $12 per hour, and she starts off making 0, which kind of makes sense because she didn't do anything yet, so why would we pay her? And we could write this as a linear relationship by identifying the rate as $12 per hour and the beginning amount is 0, as y equals $12 per x number of hours, starting at 0. You don't really need the plus 0. That's a little bit weird, but it's not wrong if you have it. And another way to interpret that might be maybe E for her earnings, or B for Brittany if you like, is equal to $12 per, and in this case you might want to use H for hours, or you could always use T for time. In number 12, the account balance for a college student based on the weekly spending patterns. They're spending at a rate of $110 per week. It's going down the money in their account, and they're starting when they went away to college with $2,000. So if you have any siblings that go to college, this is a very common type of situation. It's often the case they're calling home for money because they burn through it pretty quick. So our rate of change is a decreasing rate. Y equals a decrease of $110 per every week X, starting at 2,000. And if you wanted to write it in a more real-world context, you might want to say B for the balance in their account, and you might want to say starts at 2,000 and is decreasing at a rate of $110 per, I guess I would say W for week. It depends on how you'd like to interpret it. So we technically use the commutative property of addition there because you all know that subtraction is the same as adding the opposite. So we could have said 200 plus negative $110 per week, but I just wrote it as subtraction. If you work on backwards to some of the more mathematically based questions, which in my opinion are kind of not getting the most out of your time, in number 10, when we tell you that the rate of change is negative 1/2 and the beginning amount is 5, you'd write y equals a decrease of 1/2 x plus 5. And you could have used the commutative property to reorder that. In number 11, you might have written y equals 3x less 4 if you knew that the rate of change was 3m. We're adding 3 over and over again, starting at negative 4. You're not wrong, or you may have suggested too, isn't subtraction the same as adding the opposite? And might I have wanted to write this as y equals 3x plus negative 4? That is mathematically correct and appropriate. And as we suggested a moment ago, you could say, why don't we write it as y equals start at negative 4 and add 3 over and over again X number of times, and wouldn't that have a greater interpretive ability to it? And I do so believe. Try number 13 and 17. Pause the video for just a moment and see if you could write out those linear relationships appropriately. Assuming that you paused the video and worked on 13 through 17, my hope is that for number 13, you're representing a linear pattern with a decrease of 4 over and over again, starting at 0, as y equals negative 4x plus 0, or simply y equals negative 4x. We don't need the plus 0. For number 14, similarly, you have a rate of change of 2/3. We're adding 2/3 over and over again to an amount starting at 0. So you could have y equals 2/3 x plus 0, or simply y equals 2/3 x would be a more acceptable or a more an easier way to look at that relationship. In number 16, the rate of change is 1, and we're starting at 0, so y equals 1x plus 0. And there's a lot of extra numerical content in there. We don't need the coefficient of 1 in front of x. We know that an x with no coefficient is automatically 1, and we don't need the plus 0, because if you don't show you're adding anything to it, you'd have to know that you're starting at 0. Y equals x would be the most appropriate presentation. In number 17, if you have a rate of change of 0 and it's 70 degrees, if you think of y equals mx plus b and you know that your rate is 0, you might want to write y equals 0x's plus 70. But if you're adding 0 over and over again to 70, it's just going to remain 70. So this is often my San Diego example. In San Diego, it's supposedly beautiful. The weather's always 70 degrees every day. So it's a real easy place to be a weatherman. You just say, hey, the temperature this week is going to be 70 degrees, or temperature on Monday will be 70 degrees. And on Tuesday, it'll be 70 degrees. And on Wednesday, it'll be 70 degrees. And it just never changes. There's a zero change happening there. Cool. Let's flip to the other side of the worksheet. Clearly, we have a linear pattern because it's graphed to be a straight line. And if we want to write the equation of a linear pattern, we need to know m and b, y equals mx plus b. Or more appropriately, we need to know the rate of change, the constant rate of change, and we need to know the beginning amount of the y-intercept. And that will describe the entire relationship. So if we were to begin with the rate of change m, similar to what we saw in yesterday's lesson, we'd want to compute the rise over the run from the 2 points that we're observing at. The first point, as I reads the graph from left to right, happens at 1 unit at a time from now at a measured amount of 4, 1, 4. And we go up 1, 2, 3, 4 boxes, and each box apparently represents 1 mile in distance. We're measuring miles on the y-axis, and we're going over 1, 2, 3 boxes on the x-axis, and the x-axis is measuring time in hours. What a surprise! 90% of the time, the x-axis is time. So our rate of change is going to be an increase of 4 miles every 3 hours, or we could write that as 4 over 3, as we've been given. The y-intercept is what's kind of new today because we want to identify the beginning amount. And the beginning amount is the measured amount at time 0. So if we were to look at our graph to identify the beginning amount, we would want to observe the y-axis. That could have been done a little more neatly. And we'd want to find out where does our line start along that y-axis, or where does it intersect the y-axis, is another way of saying that. And it appears as though it's starting at a measured amount of 2. So at time 0, this relationship has a measured amount of 2. So now that we have the initial amount b along with the rate of change m, we could write that this relationship is a result of measuring 4/3 an increase in miles x starting at 2 miles. Or again, if we observe the titles of each of the axes, we might prefer to say that the distance d is a result of going up 4/3 of a mile every hour. You could either use h for hour or t for time, starting at 2. And again, you could have used the commutative property there to say, Tooch, why don't we say that it is starting at 2 miles and we're going up an additional 4/3 of a mile every hour. And that might have been easier to interpret or more appropriate. So writing a linear equation from a graph requires that you identify the y-intercept along the y-axis, the initial amount, and that you compute the rate of change if it's not given to you. Awesome. So now that we're able to write the linear equation by observing a linear pattern graphically, let's take a look at what happens when we are looking to write the linear relationship, but we're giving it as a word problem. So number 23, similar to 24, we are asked to write the equation of a line. So immediately I'm thinking y equals mx plus b. That's the most popular presentation. You could think y equals a plus bx if you prefer, and we have to find the rate of change, the amount being multiplied by x as well as the initial amount. We're told that the rate of change is the decrease of 2, and we're going through the point -1, 4. So we have to be careful here because -1, 4 does not give us the initial amount. It actually gives us the amount 1 unit of time ago. So we're going to have to use that information to find b in just a moment. I made an error here. I wrote m is 3. It should actually be -2, so let's correct that. And in order to find b, given a measured amount at some point in time along with the rate of change, we're going to have to substitute into y equals mx plus b for y, m, and x in order to determine what b is. Y is the measured amount at some point in time, and the point in time that would be given to work with was 1 unit of time ago when the measured amount was 4, so we're going to put 4 in place of Y. And we're going to substitute in that M is -2, it's a decrease of 2 over and over again, and it's a decrease that's been represented 1 unit of time ago, so we have to put -1 in place of X, and then we can solve for B. When we simplify, negative times a negative is a positive, so we actually have to put 2 into the beginning amount to determine why it measured 4. So if we subtract the 2 from both expressions, we find out that it should actually measure 2 right now. If 1 unit of time ago it measured 4, and it's going down by 2 over and over again. So now that we know B and we know M, we're able to write Y equals -2X starting at 2 plus B. Very cool, ladies and gentlemen. So now that we reviewed once again how to write a linear relationship from a word problem where you're given the rate of change along with some point in time, you have to identify the rate of change and use the information you've been given to solve for B. See if you can reproduce that same work for number 21 and 22. Please pause the video and give them a shot using 23 and 24 as model problems. Assuming you paused the video and you tried it on your own, when we take a look at number 21, we have a relationship whose rate of change is 1. And we know that 3 units of time from now it's going to measure 2. And if we substitute that information as Y, M, and X, the point of time gave us our X and Y quantities. Y was 2. It's a measuring 2, 3 units of time from that as a result of going up 1 over and over again. So what we know is that it has gone up 3 from the beginning amount, and the result is that it measures 2 in total. So if you take away the 3 that it has gone up, you'll notice that it must have started at -1. Now that you know B and M, you can substitute those quantities in to the relationship Y equals mx plus B, and you can say, knowing that the rate of change is 1, Y should equal 1x, and knowing that we started at -1, it should be -1. For number 22, the questions we prefer to do, the actual applications questions, if we are looking at a linear pattern of water being filled into a pool by a hose at a constant rate of 75 gallons per hour, and after 4 hours there's 525 gallons in the pool, written as a point on a graph as 4, 25, points on graphs are always x, y. So we're telling you at what time we measured it and what the measured amount was. We can substitute that information, the rate of change, along with the measured amount 4 units of time from now, to substitute and determine what B is, how much water was in the pool when we began filling it up. Substituting in a total of 525 gallons for Y and 75 for the rate of change M, along with the fact that we've been filling it for 4 hours, we can solve for the beginning amount. Simplify 75 times 4 and get 300. 300 gallons must have been added to this pool over 4 hours. And subtract out the 300 from both expressions, and you'll find that the pool must have had 225 gallons in it when we started. You could write that as Y equals the measured amount, in this case of gallons, in the pool as a result of going up 75 per hour X starting at 225. Or if you wanted to use the commutative property to give it a more interpretive presentation and you wanted to change the variable so it makes more sense, you could say G for the number of gallons is equal to starting at 225 when we began to fill the pool and increasing at a rate of 75 gallons per hour. Ladies and gentlemen, this was the lesson on how to write the equation of a linear pattern, a repeated addition pattern, by identifying the rate of change, ladies and gentlemen, this was the lesson on being able to write linear relationships or repeated addition patterns, having to identify the initial amount B, or compute it, not knowing what the initial amount was, the value at time 0. Most importantly, you have to be able to identify the rate of change or possibly compute it. And once you know the rate of change, then you're going to have some measured amount at some point in time, doesn't really matter when, and you can use that information to determine what the beginning amount must have been. Once you know B and M, you can write an appropriate linear relationship. Hope that makes sense, and I'll see you in class. Take care.